Okay, folks, today's class is all about this special force called the drag force. And what happens is we've been ignoring air ever since, the beginning, right? When we did projectile motion, we ignored air, right? We always ignored air. Remember, it was always just this perfect ideal case. You shoot things off at 45 degrees. But in real life, when something falls, let's say we have a ball and it's falling down. Can you draw a free body diagram on this ball at t equals 0? At t equals 0, what are all the forces acting on the ball if it starts from rest? If V initial equals 0, what are all the forces acting on that ball? Do that for me right now. Draw all the forces acting on the body. And it's not a trick question. You probably are done by now. Okay? So draw all the forces acting on that body right now. And what do you get? mg down. And that's it. Whoa. My thing is not calibrated very well. mg down is it, right? Let's try something here. So we got mg down, and that's it. mg, that's it. Okay, you're done. There is no other force because it's not moving yet. But could you draw me a free body diagram later on? T equals T1. It's some other time. And V is not equal to 0. V is at some function of time. But if some of you read the book ahead of time, you kind of know that eventually what's going to happen to this speed. Eventually, when the faster you go, what happens to friction? Friction's going to get greater, greater, greater. Eventually, Zach, what's going to happen? Right, that's called terminal velocity. So I want you to draw a free body diagram before that happens. I want you to draw a free body diagram on the same ball, right, with the same mg down, but this time, what force are you going to include, or what are you going to add to that drawing? Some drag. Now, how would I draw that arrow? Would that arrow be greater or lesser? Man, this should have been green or something. This would have been great as green, and then red for friction. So look what I did. I made this arrow intentionally smaller. Now, I call it the force of drag. In your textbook, the Knight textbook, they just call it letter D. So either one. It doesn't matter what you choose to call it, but I like to call it the drag force. The drag force, okay? Now, in the book, it describes the variables that drag force would incorporate. So let's think about it. If you're falling through the air, what variables would affect how much friction or how much air resistance there is? The surface area of the object itself. So that makes sense, doesn't it? I mean, seriously, that's what parachutes are all about, right? Get a big enough surface area and your terminal velocity is a manageable 7 miles per hour, and then you just float down, and at the last minute you pull 2 ropes and you kind of like get a little uplift for a split second. If you time it right, you don't even hurt your knees when you land, right? Because of the surface area of this big, huge thing, right? So it's the surface area. What else do you think it is? It's on the board. What else? The velocity that you're actually moving. Now think about how weird that is. This arrow right here is growing bigger and bigger and bigger as time goes on. Why? Does the surface area change? Name some other stuff that would affect how much friction there is in the thing. We already talked about that, so we don't want to keep mentioning the same thing. We want to do something new.
The medium?
The medium. What do you mean about the medium? Right. So how about stuff like the density of the fluid you're going through? Think about if the density of the fluid, like air, is kind of small compared to water, right? So what would be this friction if you were traveling through thick air versus thin air, right? So that means if you're jumping from the high altitudes like that Red Bull guy did, and he actually like jumped from practically space from this crazy balloon way, way up there, think about how thin the air was up there. The dude had to wear a spacesuit, right? So the air was so thin. Imagine how little the drag force was at that time because in the beginning the air was so thin. So it was the density of the fluid that you're going through, the surface area, but then there's something else besides just the surface area and the speed, of course. What else? There's got to be something else because I have two cars that have the same surface area, but one car gets less friction, better mileage. Aerodynamics of the car. So there is a drag coefficient that we throw into the equation, okay? So not only do we have the surface area of the object, but the variables that will affect this thing is pretty much 1/2 times this CP. It's kind of like this constant, and then the surface area, right? And then it's the velocity, and sometimes it's the velocity squared. Now that bites, because the velocity squared makes for a really horrendous integral, a really tough mathematical thing to solve, okay? So bad so that a lot of physics books now aren't even doing it. So I'm going to solve an easy one, and when we do our lab, we're actually going to try to solve the more difficult one, but probably, unless you're way smarter than I am, you actually would have to go online and find in an integral table the integral that goes with v squared. So I'm actually going to demonstrate one with just v. Now what do I mean by that? Some friction is dependent on v, the speed. How fast you go? If Jake doubles the speed, he doubles the frictional force, the drag. The drag is doubled when the speed doubles. But most things in real life, like cars and human beings, skydiving, it's v squared, not v. And that bites, because then the integral is bad. Okay? I'm going to show you the easy one and only expect you to know how to do the easier one where it's just v, not v squared. But what is this thing? What is that guy? Okay? You know what's hiding in there? The density of the fluid and this drag coefficient is all thrown into this arbitrary constant. Okay? Every book kind of describes it a little bit different. I've seen some books actually say that the drag force is equal to 1/2 times the density of the fluid times the area of the object times v squared and then times some kind of drag coefficient. I've seen lots of different ways of writing this down. This book, the book you're using, is incorporating the density of the fluid in there with the shape of the object. Okay? So can you imagine what shape a water drop takes when it's going through air? It doesn't look like a drop. It looks more like a red blood cell where it's kind of like this weird oval shape. Because that makes sense from the surface tension of the water molecule plus all this air pushing up against it. It makes its own little, kind of like a little parachute. All right? So like a weird shape. Okay? It doesn't look like your typical raindrop, stereotype raindrop. It's like the human heart doesn't look like a heart, you know? So that kind of shape. Think of two different cars, a Volvo and a, you know, some kind of Lamborghini, and think about the aerodynamics, the shape that the car made, and you can kind of tell it's not just the area, it's how it's streamlined. Like a semi-truck. Have you seen what they're doing with semi-trucks now? Where behind the truck, instead of it just being a box back, they actually taper it back with sides so that the back of the box, if this is the truck and it's driving down the road like this in the semi-truck, there's all this drag showing up behind there. It sucks it back there. When I'm riding my motorcycle, I just get kind of sucked into this little vacuum. Well, that makes poor gas mileage because it's not just the surface area, but it's the shape of the thing that's going to factor in what that constant's going to be like. So the surface area of two trucks could be exactly the same, but if one truck puts kind of like a fin behind it, I don't know how to draw this thing sideways, but it's kind of like a little plastic thing behind it that tapers off so it actually comes to a point. You'll see it on the back of helmets on slalom skiers. Instead of just a regular helmet, they got like this teardrop back to it so that it goes back behind. That stops a little bit of the drag. It stops a little vacuum that forms behind these square things. Okay? So it's not just the surface area, but what happens behind it that will also affect this drag force. Okay? So hopefully you got a flavor of what this this drag force is caused by, and what variables? The area, the speed, and a bunch of constants like the density of the fluid and what the aerodynamic shape of the object is. So you got that in your mind? What variables will affect this force? Okay, so let's go on to another page here and do that. This time, let's draw a free body diagram. And we'll make it a little easy this time. Instead of all those crazy constants, let's just call this the drag force, and let's make the drag force equal to an arbitrary constant that involves all the other constants, okay? So what do we learn? There's a constant of the aerodynamic shape, there's the density of the fluid, there's the area of the object. Let's make that all just one constant and call it beta. And then let's make this even easier. Instead of beta v squared, like what's probably going to happen in our lab today, let's make it beta v. All right? Let's make it a little bit easier just so we can kind of stay in the shallow end and blow bubbles a little bit with this integral before we get into the real difficult integral. Okay? So, why did I make that arrow up smaller than the arrow down? What's going on at this moment? Right, it's still accelerating down, but is it accelerating at 9.8 anymore? No, because the net force isn't mg. You see, in the beginning, when we just had mg down, if there was no air, this would be the free body diagram. If there was no air, this is it. We're done. So the sum of all the forces causes the mass to accelerate. I'm going to sum them all up, and I get mg equals ma, and the m's cancel. I'll be damned, everybody accelerates at 9.8 no matter what your mass is. Why? Because the mass that wants to remain at rest also is being pulled down toward the Earth. And if you have twice as much mass that wants to remain at rest, you also are getting pulled by planet Earth twice as much. The two effects cancel each other out. That means gravitational mass is equal to the inertia mass. Einstein spent years telling you that that's not a coincidence. Something really weird happens around mass. Mass not only causes gravity, but mass also warps space-time around it. Cool stuff that Einstein spent a lot of time talking about. Okay? Now, that's what would happen if there was no friction. But now, go back to this picture over here. Now there's friction. Now, use the same formula. Remember the recipe? Draw a free body diagram. What's the next step? Pick a positive direction. Always try to pick the winner. So who's the winner? Up or down? Down. So take down as positive, up as negative. So what's the next step? What should I do? Break up into components? Now there's nothing to break up. So what's the fourth step that I know you guys got memorized now? Step 1, draw a free body diagram. Step 2, break up into components. Step 3, pick a positive direction. Step 4, write down F equals ma without even thinking. The sum of all the forces causes the mass to accelerate. So do that for me. You know the winner, you know the loser. What are you going to write down next? What's the next line that you write down because you know how to obey the sum of the forces equals ma? What are you going to write down? Got it? mg minus, and let's just write it down as beta v. mg minus beta v equals ma. Okay? All right. Now, this is where I take a little pause and I ask you a qualitative question. If you were going to graph velocity as a function of time, I want you to try in your notes right now, before you watch me do it, to graph what this would look like as time passed. At t equals 0, what was the acceleration? 9.8. So that means the slope is pretty steep in the beginning, right? 9.8 is the slope of that line. We're saying down is positive, so that's why it's like up like that. Okay? Now, what does this graph look like as time goes on? Think about it for a minute. Look on with somebody next to you. If you're home alone right now, look on your own paper right now and see if you can come up with a graph on what this thing looks like. Is it ever actually straight? No. So don't draw anything straight, because straight means constant, and this is never going to be constant. Maybe at the end something weird happens, but it's never technically ever constant. Okay? So everybody got it? I'm now going to give you the answer. Check your paper and see whether or not you came up with this graph. 9.8 instantaneously in the beginning, but it immediately starts tapering off. And what does it approach at the end? Right, that's what's called terminal velocity. Right here we'll call it VT, terminal velocity. Does it ever actually hit it? No. It's one of those asymptote things where it approaches it forever. It keeps getting closer and closer. Why? Let's talk about F equals ma. Guys, if mg is down and you got this frictional force up, what's happening to the size of this arrow here? As time goes on, what's happening to the size of that arrow? It's getting bigger. And what size is it approaching? mg. So eventually you can lie and say that for all practical purposes, the frictional force will eventually, after a long, long time, equal mg. Agree? Now what's the net force when that happens? And therefore, what's the acceleration when that happens? And therefore, if there's no acceleration, what can you say about the velocity after that? Right, and that's the definition of terminal velocity. So what's the answer? What's the terminal velocity? Come on, do algebra. This is going to be equal to 0 here now. So after a long, long time, what is the velocity going to be? No numbers, man. Just do algebra. What is that velocity going to be after a long, long time? You hopefully right now are setting A equal to 0. So what is V? What is V terminal? What does that equal? That's it. That's right. mg divided by, we'll call that beta so that you don't call that a b. Okay? mg over beta is the terminal velocity. All right? What if it was v squared, like it's going to be in our lab? What if this up here was a v squared instead of a v? Then what would terminal velocity be? Square root of mg over beta, right? What if it was v cubed? We had some weird thing there. Fluid was really thick. And, you know, when you doubled the speed, it was 4 times the force. Then it would be squared. What if you double the speed and it's 8 times the force? Then it's cubed. So that you could have anything happening here. Okay? All right. So I want you to look at this equation for a minute and ask yourself, how could I solve for velocity as a function of time? In other words, what if somebody asked me, hey, how fast is it going right here? At this time, how fast is it going? Or how fast is it going right here? Or how fast is it going right at this time? How fast is it going? How would you solve for that? How would you effectively give me an equation that goes with this graph? What equation goes with that weird, huge asymptote graph? It's some weird integral, isn't it? It's probably got something to do with natural logs and e to the, because those are the ones that eventually approach but never hit things. Okay? So what we're out to do right now is to do that integral. So let's change pages and start from scratch, okay? And go right up here, the sum of the forces, mg minus beta v equals ma. But I want to write a different way. What's another way of writing the instantaneous acceleration? Because this acceleration is not constant now. It's not like those kinematic formulas from other chapters. This a is changing as time goes on. What is it? I was looking dv dt. The derivative of velocity with respect to time is another way of saying the instantaneous acceleration. So, if anybody asks you to write Newton's second law in differential form, I just did that. Look at it, stare at it. When the minute you hear differential form, it means every time you see an a, write it as dv dt, because that's the differential form of a. This a is constantly changing. I said that really badly. This a is changing as time goes on. A is getting smaller and smaller, 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 until eventually a approaches approaches 0 without ever hitting it. Okay? All right. So I'm going to do the integral for you. You can help me out, give me some suggestions, make sure I do the math right. But here's what I'm going to do. I'm going to do what's called integral by parts, right? And I'm going to do a definite integral. So here's some thing. At t equals 0, let's make life easy and say the initial velocity equals 0. In other words, something started from rest. That way our initial conditions are that way. We don't have to find the arbitrary constant or put that into find c for the integral. We can just do a definite integral and say that the original time was 0 and the original velocity was 0. Okay with that? That's going to make our life a little easier. So I want you to imagine a skydiver falling out of an airplane or a hot air balloon. So she's pretty much stationary. At t equals 0, v equals 0, and then starts from rest and goes faster and faster and faster and faster and faster. Now there's another integral you could do. A meteor. A meteor is going crazy fast. Let's pretend infinite speed. And then when it hits the air, what's the air going to do to the meteor speed? It was starting off going really fast, and then what's the air going to do? It's going to slow it down to terminal velocity. Think about what that graph would look like, right? That's kind of like a mirror image of what I just did, right? Now we got this crazy velocity, right? And then it dies out to terminal. Now, for a skydiver, I'm starting from 0, and I'm going faster and faster and faster and faster, but then I eventually don't go faster. Okay? You got the visual? All right, so what do? How about this? Why don't we bring the dt up and divide it by m, and then over here, dv all divided by mg minus beta v. We okay with that? Check my work, make sure I did that right. We good? Okay. So we could integrate both sides. We could clean it up a little bit. I've had people, first thing they did was divide everybody by m first. So I know people who did this. G minus beta v over m equals dv dt. In other words, the m went away on the other side. And they integrated that one. They did dt came up, right? And then they had dv divided by g minus beta over m v. And they did it that way. Okay? I've had a lot of people do it totally different. They divided everybody by beta so that nobody would be near the velocity. And then they ended up with this one. So they did mg over beta, right, minus v equals dv dt, and then they divided both sides by beta, so this was m over beta. Okay? So there's lots of ways you can do this, and none of them are right or wrong. So any way you want to do this, you're still going to get the same answer if you do it right. So whether one's easier than another, I don't know. Now that I'm in that mood, I'm going to... That's cute. I'll try this one on the bottom here. Let's try this one. Okay? I got beta dt over m equals, so if I do this right, dv divided by mg over beta minus v. Check my work and see if I did that algebra right. I brought everybody on this side underneath the dv, and then I multiplied both sides by beta and divided both sides by m dt. Did I do that right? Check my work. Okay, so I'm liking it. So what if I integrated both sides? Can you guys help me with this integral? What if I integrated this from 0 to some final t? And what if I integrated this from the initial velocity. But what was the initial velocity? 0 to some final velocity. And that's what my goal is, to find that final velocity. That velocity as a function of time. Okay? All right. What do I do? What do I do? What is the integral, a definite integral of beta m, that's both constants, so they can come out of the integral and go over here, dt. What's the integral of dt? T. So I'm just going to stick in t final minus 0, which is just t. Okay? So I'm just going to make this beta t over m, where t is really the final time, not the time interval. Everybody see what I just did on that side? Okay? What do I do on this side? Okay? Now, if you're a little rusty on integrals, you might not know what the integral of that mess is. Okay? But the answer to this is, evaluated from 0 to v final, would be the natural log of this stuff, mg over beta minus v, the natural log of that stuff, times 1 over the derivative of what's inside. What's the derivative of what's inside here with respect to the v? Negative 1. 1 over negative 1, right? 1 over whatever was here. Now, look and see what the other option was. Look at over here. What if I had done this integral? Then what would have been the derivative of this bottom part? 1 over negative beta over m. Get it? So I still would have ended up with that beta over m thing over here by doing it over there. So it never fails. You know, even if you don't clean it up like I did, you still end up with beta t over m on one side and that on that side. Everybody okay? All right. Now, let's evaluate it by sticking these numbers in. Okay? So this is negative 1. The negative 1 can go on the outside here. And then let's evaluate the natural log of, in parentheses, mg over beta minus v for v final, and then minus, and then put 0 in for v. Okay? So it looks to me like it's the natural log of mg over beta minus v minus, remember how you, when you do a definite integral, you subtract the bottom limit there. And then what is it? Put 0 in. What do you get? Right, just the natural log of mg over beta. Okay? And the whole thing has got a negative 1 on one side. So I'm going to make life a little bit easier and put the negative on the other side. So I'll do minus beta t over m equals, now, I don't know if you guys remember that natural logs, like logs, are really exponents. Natural logs are the opposite of e to the, right? And regular logs is really 10 to the, but the opposite of. Get it? So, when you subtract a natural log from a natural log, do you remember that it's really exponents? So what are you really doing when you subtract exponents? We're dividing. So another way I can write this is this. The natural log of mg over beta minus v divided by mg over beta. Did everybody see what I just did? This minus that is the same as the natural log of this one divided by that one. You guys remember that little natural log trick? When one natural log is subtracted, the other natural log is the same as the natural log of one divided by the other. Because they're exponents, and we subtract exponents. Okay? We're 2 steps away from getting v all by itself. It looks a little scary, doesn't it? All right? So, the next step, I'm going to copy this onto the next page, unless there's a way to extend this page. Is there a way? Yeah, Let's try it. Extend that page. Okay? And let's try to write down what this is. I got minus. Well, before I do that, how do you get rid of natural logs? Right, the opposite. So everything in algebra, you just got to know the opposite. The opposite of natural log is e to the. So if I do e to the minus beta t over m, that equals e to the natural log of all that crap. But the natural e to the natural log of that crap is the stuff in the parentheses. So that means e to the minus beta t over m equals mg over beta minus v, all divided by mg over beta. You see what happened? I just got rid of the natural log. Now the rest is just algebra. If I multiply both sides by mg over beta, I have mg over beta times e to the minus beta t over m equals mg over beta minus v. My goal is to get v all by itself. So here's my suggestion. Bring the v over to this side and bring all this crazy stuff over to that side. Okay? So let's see what that looks like. It looks like I'm going to have v as a function of t equals, here we go folks, the punchline, mg over beta minus, because they changed the sign, mg over beta times e to the minus beta over mt. If you want to clean it up one more step, you could factor out the mg over beta. You don't have to do that, but you could say mg over beta times 1 minus e to the minus beta t over m. Folks, that's the integral. I would need for you to be able to do something like that on a test someday. Okay? So practice my way. Don't memorize the actual letters. The letters will be different on a test, but know and understand how to do something like that. For our lab, we got one more difficult thing. We have an integral that I'd have to actually look up on a trig table or an integral table to find, because that v squared really gums up the stuff. But the essence of the same thing is this equation. Folks, this is the equation that goes with that graph. That graph of velocity as a function of time, this is the equation that is a mathematical expression of that graph. Now, let's see if it's right. Let's see if I'm feeling good about life. Okay? So, let's plug in some conditions. At t equals 0, what should the velocity be? Let's find out. Let's see if it worked. So, put t equals 0 right in here. If t here equals 0, then it's e to the minus 0. What's e to the 0? 1. What's 1 minus 1? Sweet, the velocity is 0 when the time is 0. Let's have some more fun. What if the time is infinity? What if the time is so friggin' big that the time is, for all practical purposes, infinity? What's e to the minus infinity? 0. I don't know if most people knew that, but e to the minus infinity is equal to 1 over infinity. And 1 over infinity equals 0. The bigger the denominator gets, the smaller the number gets. So 1 over infinity equals 0. So at t equals infinity, then this is 0. So it's 1 minus 0, or 1. What's mg over beta times 1? And what is mg over beta? Look at your notes. What did you find out first thing before I even asked you about the integral? What does mg over beta equal? Terminal velocity. I'm feeling real good about this equation. At t equals 0, the velocity was 0. And at t equals infinity, the velocity is a constant mg over beta. Isn't that sweet? As time approaches infinity, the speed approaches the weight divided by all those crazy constants. Now remember, beta is a symbol I made up to represent the coefficient of drag, the density of the air, the area, surface area, all those constants that would affect your aerodynamics. Okay? Big thing is surface area. All right. So you like it? Scary? A little bit? Okay? But practice this. Just rehearse it. Know that you should be able to do something like that and get an equation like that. Okay? If anybody takes the second half of this course, we're going to have the same phenomena happen when you discharge or charge a capacitor. The closer the capacitor gets to fully charged, the less voltage difference there is. And the less voltage difference there is, the less current there is. And the less current there is, the slower it takes to charge. And so it never actually quite gets to 100% charged. It just gets close enough for all practical purposes for us to go, yep, it's charged. Right? And we can actually figure out how long it would take. So look how powerful this equation is, folks. Everybody stare at this equation for a minute and realize that if I ask somebody in the room what the time is, or I tell them the time, and I say, okay, after 1 second, a 1 kilogram ball with a constant of 0.2, a 1 kilogram ball after 1 second, or after 5 seconds, or over 10 seconds, how fast is it going? And how long does it take to get so close to terminal velocity? Pretty much it ain't really speeding up anymore. Do you know how elegant this is? Think about it. After 2 days of falling, it's still not reaching terminal. It's not there yet. It's so close that for all practical purposes we can say it hit it, but it's a lie. It never actually hits it. Because what happens after 2 days? The drag force is almost 99.9999999 what the weight is. So what's the net force? 0.000000001. And then divide by the mass, and what kind of acceleration do we got? 0.000000001. Right? But it's still speeding up, and therefore there's still a net force, and therefore the velocity is increasing. It's just not increasing like 9.8 anymore. It's like increasing like it takes 3 days for it to speed up 1 micron per second squared. Isn't that wild? You never actually hit it. That's the elegance of this thing. We found a mathematical way of expressing this graph. It never hits it, but for all practical purposes, we can just lie and say, yeah, okay. It's been in the air for 5 seconds. So I went skydiving one time. Really a lot of fun. If you're ever going to do it, do what's called a tandem jump. If you're okay with some guy being strapped to your back who actually has the parachute on him, which means his life is in your hands, then you fall, but you get to experience free fall. I jump out of this airplane and I'm like upside down, and I don't even feel upside down, and the airplane looks like it's just getting sucked away from me because actually I'm falling and the airplane's pretty much in the same spot. It's a great experience because you actually get to experience this feeling of weightlessness. But, you know, after 5 seconds, I didn't feel weightless anymore. I felt like I was floating on a big air cloud. I'd grab it with my hands, and it wouldn't feel like air. It would feel more like liquidy than gas. You know? It's like if you put your hand out the window while you're driving, try going out the window. Try driving at 130 when no one's looking. Put your hand out the window, and you'll know how this air feels when I skydove, whatever it's called. It's this really weird feeling. So I'm going about 120, 130 miles per hour, right? And it didn't feel like I was falling anymore. It didn't feel weightless anymore. It just felt like I was floating on a cushion of air. And every time I looked, the ground was, you know, a little bit bigger. The farmland was a little bit bigger. But I never got the sense of falling, right? Because we pulled the chute while we were still a mile up in the air. So I never got that sense that the ground was coming toward me or anything like that. If you go to Darien Lake on the Sky Coaster, you actually get to see the ground come toward you. But this was just a pretty picture, very surreal. It's a really fun experience. If you ever get a chance to try it, I highly recommend you just do it, just so you know how that terminal velocity feels. Because after about 5 seconds, literally 5 seconds, I was close to terminal velocity enough where I really wasn't speeding up very much at all. It only took 5 seconds for me to get to a speed that was for all practical purposes constant. Is that kind of neat to think of? All right? So this integral is really elegant, and this thing is really good. So let's do one more quick step just to freak you out. Okay? What would I do if I asked you, where is the object at a certain amount of time? Right. So every time you see velocity, think of the velocity as dy dt, where y is how far it fell. And now we got to solve for y. Okay? So the original distance is where you dropped it from. So if you're dropping this thing off of a cliff, y initial equals whatever the height of the cliff is. It might be 30 meters up in the air. And then you drop this object and it falls. If I want to know where it is at any given time, what do I got to do? I got to take that equation and I have to integrate. So that means dy equals mg over beta minus mg over beta e to the minus beta t over m dt. And if I integrate this from the original position, 30 meters, to some final y, and then I integrate this from 0 time to some final time, I can integrate that thing and end up with a weird equation that solves for position. And I would know where it is at any given moment. Okay? You can kind of see what it would be. It would be mg over beta times time, and then minus mg over beta e to the, what happens when you put, what's the integral of e to the minus beta over mt? Do you remember what that is? E to the minus beta t over m times 1 over, I think it's 1 over, which is minus m over beta. Do you remember that? If I just gave you this, e to the minus beta t over m, what's the integral of this? Do you guys remember how to do that? What's the integral of e to the minus beta t over m dt? It's a e to the minus beta t over m times negative m over beta. Did I do that right? Okay. And then it would be a definite integral, and then you'd have to put 0 down here and some final time up there.
Doesn't the t go away? And not go away, but isn't
It's gone here.
it? Yeah.
Yeah. There's no t there.
Okay.
It's just minus m over beta. It's the derivative of this 1 over that.
Okay, that's what I thought.
Yeah.
Thanks.
There's no t there.
Oh, because we're integrating.
Integrate. Okay? All right. So that would be something you can just try on your own, and you should be able to get an equation for the place. So look how powerful this is. I could tell you not only how fast it's going. You tell me the time, and you tell me all those crazy constants. I could tell you where it is and how fast it's going. You just tell me the time. Isn't that kind of neat? All right. So one more crazy thing, and that is this. Just in our lab, all right, in our lab, we have the mass, and sure enough, gravity's pulling it down. But unfortunately, in our lab, we have some constant. And what's that beta? That beta is probably equal to 1/2 times the coefficient of drag coefficient times the area, right? And it's v squared equals this drag force. That bites. So if I want to save myself a little writing stuff and call it beta, that's fine, but there's beta v squared. And that integral is just more difficult. An integral where, I got to be honest with you, I had to look it up. I'm just too rusty to know all these things by heart. I knew the 1 over x equals natural log x. I knew that one. But this one I had to look up. And so will you. So for your lab, one part of your lab is to find the integral that you could use to integrate that to get v as a function of time. and then attempt to take the integral of that to get the position as a function of time. And that's what our lab's going to be. Here's what we're going to do. We're going to take some coffee filters, just regular stupid coffee filters, and we're going to drop them down the stairwell. And these coffee filters, we're going to be a little clever about this. These coffee filters will remain with the same effective area. This right here, this effective area of the coffee filters. This is like the surface area from here to here when it's flying through the air is that much area, right? Now, if we put another coffee filter inside that coffee filter, for all practical purposes, the area and the coefficient stayed the same. The only thing we changed was the weight. Are you with me on this? So therefore, we should be able to graph the mg of the coffee filters versus velocity, or vice versa. Okay? So how about if we do it the other way? Terminal velocity of the coffee filters versus mg. I think the terminal velocity depends on mg, so let's not do this one. Let's do this one. Well, what do you mean? Didn't I just spend all this time telling you you never actually hit terminal velocity? Now what am I telling you? We're going to do a lab and we're going to graph terminal velocity versus mg. How are we going to get terminal velocity? And the answer is we're going to pretend it got so damn close to terminal velocity, we're going to just call it terminal velocity. So here's my idea. We get somebody tall, right, to hold these coffee filters out and drop them. And by the time it gets to their feet, it's probably so close to being terminal velocity that from then on, the coffee filters will be going down the stairway, and these coffee filters are going to be dropped from up here, and by the time they get to here, the coffee filters are probably going to be going close enough to terminal where we can just say it's the terminal velocity. Then we'll know this height, and you guys with stopwatches will time how long it takes to go from here to the ground. What's special about terminal velocity? It's constant. So what's the only equation we're going to be able to need to use? It's the only equation you use when the velocity is constant. That took too long. The only one is equation A, distance over time. There's no other one that makes any sense because all the other ones have an acceleration in it, and I just told you the acceleration was 0 because the velocity was constant. So all you got to do is take this distance and divide by the time it took to go that way, and you're going to get the velocity of the fall, and we're assuming that it is the terminal velocity because if we get somebody tall enough to drop it here, by the time it gets to their feet, for all practical purposes, it's terminal. So now we can graph terminal velocity here versus mg. Do you think you'd get a straight line? The integral that we just did? Yeah, we would get a straight line. But no, real life isn't as pretty as physics class with everything all constant and clean and you got this perfect sphere in a vacuum kind of stuff. No, in real life, you know what this is going to look like? Yeah, it's going to curve. Which way is it going to curve? Concave. If the weight, if the velocity, it's v squared is the straight one, right? So is it like this? If you double mg, you don't double the velocity, right? If you double mg, you don't double the velocity. So this is probably a graph just for fun. Here's the graph that I eventually, once you realize that that's not a straight line, then here's the graph that's going to mean something to us. V terminal squared. I'll bet you that one's going to come out to be linear. And what would the slope of this line give you? I'm just making all these words up. Listen to you guys just babbling now. What's the one thing that's not included in here that we talked about in the integral we just did? Beta. So the slope of this line would be beta. And what was beta again? Beta is all this crap right here. Okay? That's beta. Okay? We got it? All right, so that's the bold plan. That's what we're going to do today in lab. But see how I had to give you that integral?